Enceladus and Europa are two icy moons orbiting Saturn and Jupiter, respectively. They are believed to have liquid water oceans, making them potential targets for future life detection missions. However, due to limited data from previous missions to these moons, researchers have conducted studies to better understand the conditions that may exist beneath their icy surfaces. Based on these studies, researchers have hypothesized a number of possible metabolisms that could exist on Europa and Enceladus if they host life. Let's look at the most up-to-date research and explore the possibility of finding alien life in our solar system. Welcome to AseeLearning. There is a lot of attention given to Mars as a possible location for finding signs of extraterrestrial life. However, if we consider the origins of life on Earth, we come to a realization that wherever there is water, there is the possibility of life. By applying this same principle to other celestial bodies in our solar system, two moons in particular stand out from the rest. These are the icy moons orbiting the gas giants Jupiter and Saturn, namely Europa and Enceladus, respectively. If you are planning to send a space probe to Jupiter's moon Europa and land on its surface, you should expect a journey of nearly 1,800 days, which is just under 5 years. Given its extreme environment, any spacecraft exploring the moon for signs of life must be able to endure harsh conditions. On its warmest days, the temperature on Europa's surface is minus 210 degrees Fahrenheit, or minus 134 degrees Celsius, and at its coldest, temperatures can drop to minus 370 degrees Fahrenheit, which is minus 223 degrees Celsius. Europa, the sixth closest moon to Jupiter, experiences not only extreme temperatures but also intense radiation levels. These radiation levels are due to Jupiter's strong magnetosphere, which is the most powerful of any planet in the solar system. Jupiter's magnetosphere captures particles ejected from the Sun. As a result, high-energy particles constantly bombard Europa's surface, causing it to glow even on its night side. According to research led by Murthy Gudipati of NASA's Jet Propulsion Laboratory, Jupiter's magnetosphere accelerates the particles and slams them into the ice. As the particles reach Europa's surface and suddenly stop moving, they lose energy and emit visible light. This radiation of light is so intense that it creates glowing on Europa's surface. Despite the presence of extreme radiation on Europa's surface, there is still a possibility of life existing beneath the ice. The estimated thickness of Europa's ice layer is between 10 to 15 miles, which is 15 to 25 kilometers, which acts as a protective barrier for the global ocean of Europa. This ocean surpasses the size of all the seas on Earth, with its depth estimated to be between 40 to 100 miles, which is 60 to 150 kilometers. We know that Europa has an abundant water supply, making it a viable candidate for sustaining life. Additionally, it has a protective shield that guards living organisms from harmful radiation. However, the question remains, how would any potential life forms acquire energy? On Earth, the foundation of the food chain derives energy from the sun, which is then transferred up the chain through the consumption of other organisms. Unfortunately, sunlight cannot penetrate the thick ice surface on Europa. In this case, we can take cues from other examples on Earth to identify potential energy sources that could support life on Europa. At the bottom of Earth's oceans, there is complete darkness. However, we have discovered that energy is available to establish an ecosystem thanks to volcanic activity. As a result of underwater volcanic activity, thermal vents open and release chemical energy from the Earth's interior, which organisms can use. This process of converting non-organic chemical energy into usable organic energy is called chemosynthesis. It is expected to be the basis of any life found on Europa, Enceladus, or any other world that lacks an abundance of solar energy. On Earth, underwater volcanic activity is formed by the convection of molten magma that occurs in the mantle, as well as tectonic plate movement. However, on Europa, things work a bit differently. Hypothetical thermal vents on Europa would be powered by the gravitational interactions between Europa and its host planet, Jupiter. Jupiter's immense gravity, which is greater than that of 1,000 Earths, causes Europa to stretch and flex, much like an accordion would be if it were squeezed and pulled. This stretching and flexing creates friction within the inner core of Europa, leading to molten magma circulating and rising up within the Moon. This magma then rises through the rocky layers until it reaches the bottom of the ocean, releasing chemical energy like sulfur dioxide into the ocean of Europa. It is this release of chemical energy that could form the basis of potential life on Europa. Life on Europa, if it exists, could possibly be either aerobic or anaerobic. On Earth, aerobic processes have been known to produce more complex organisms because they can produce more ATP. In simpler terms, if Europa's oceans contain enough oxygen, life forms could become complex, such as alien crabs or fish. This would be possible if the radiation provided by Jupiter's magnetosphere ionizes lower levels of ice in the shell, separating it into oxygen and hydrogen, as it does at the surface. In theory, this could result in high levels of oxygen in the oceans. If the oxygen supply is low, anaerobic respiration will likely be the primary form of cellular respiration. This form of respiration is less energetic, which could lead to less complex and smaller organisms. On Earth, unicellular organisms rely on anaerobic processes as their sole form of respiration. Hypothetical life in the oceans of Europa is expected to have a strong cellular binding and membrane due to its ability to tolerate a salt-brine mixture of sodium carbonate, magnesium sulfate, and ammonia, as these chemical compounds are expected to be very abundant and highly concentrated in the oceans of Europa. It is more likely that this life exists in the lower levels of the ocean near the warm thermal vents than the cooler upper levels. This hypothesis is formed because here on Earth, the temperatures where life exists are typically at or above -4 degrees Fahrenheit or -20 degrees Celsius. Any colder and even microbial life is rarely found. However, exceptions exist. The average temperature of the oceans of Europa falls within this temperature range, so it is possible for life to be found in other places, making it possible for life to exist and thrive in its salty, ammonia-infused waters. In fact, this brine mixture helps keep the ocean from freezing, because as we know, liquid water freezes solid at only 32 degrees Fahrenheit, or 0 degrees Celsius. Although there is strong science behind the theory of life on Europa, there is no planned mission from NASA or any other space agency to explore the habitability of Europa's oceans at this time of November 2023. Nevertheless, NASA is currently building the Europa Clipper, a space probe with the mission of further studying the Moon to confirm if theory is fact, and if the conditions necessary to support life are indeed present in the ocean. According to NASA, the main science objectives of the Clipper mission are to understand the nature of the ice shell and the ocean beneath it, along with the Moon's composition and geology. The mission's detailed exploration of Europa will help scientists better understand the astrobiological potential for habitable worlds beyond our planet. NASA's Europa Clipper spacecraft will perform dozens of close flybys of Jupiter's moon Europa, gathering detailed measurements to investigate the Moon. The spacecraft, in orbit around Jupiter, will make nearly 50 flybys of Europa at closest approach altitudes as low as 16 miles, 25 kilometers, above the surface, soaring over a different location during each flyby to scan nearly the entire Moon. The Jovian moon Europa is an icy world that has drawn attention in the quest for extraterrestrial life. However, it is not the only satellite of interest. Moving further away from the Sun, at a distance almost twice that of Jupiter, we reach the second gas giant in our solar system, Saturn. While the Saturnian system is well known for its spectacular rings, first observed by Galileo, there may be something even more remarkable orbiting the planet: the small icy moon Enceladus. Enceladus is significantly smaller than its larger counterpart. While Europa's diameter is about the same as the length of India from north to south, measuring at 3,100 kilometers or 1940 miles, Enceladus is only comparable in size to the state of Arizona, which is about 6 times smaller. Despite its smaller size, Enceladus bears a striking resemblance to Europa, with a large outer shell of ice and an expected ocean beneath it that spans the entire moon. However, while there are many similarities between the two moons, there are also some key differences. The ice shell covering Enceladus is thinner than Europa's. Near its south pole, the ice is just half a mile or 1 kilometer thick. This is good news for any potential expedition to explore the Enceladine Ocean, as drilling would be less intensive. However, drilling on this moon would still require a massive power supply, and laser technology would likely be used. This is less mechanically demanding than conventional drilling, but still requires a lot of energy. Additionally, Enceladus is an extremely cold world with temperatures as low as -330 F or -210 C. Any space probe sent to explore it would need to be capable of storing energy and operating in these extreme conditions. Enceladus and Europa are both very bright, but the reason behind their luminosity is different. Unlike Europa, Enceladus is not constantly bombarded with intense radiation. Instead, fresh ice on Enceladus' surface causes it to glow. This fresh ice is formed due to the plumes of liquid water that erupt from the moon's internal ocean. The water plumes shoot out into the orbit of the moon at an astonishing speed of 800 miles per hour, 400 meters per second, which is faster than the speed of sound on Earth. These plumes contain water vapor, methane, salts, silica, carbon dioxide, and trace amounts of either nitrogen or carbon monoxide. The water vapor either falls back onto the moon's surface or becomes a part of Saturn's E-ring. When the material falls back onto the moon's surface, it reflects most of the sunlight, leading the world to resemble a round piece of chalk. This reflection also leads to the extremely low temperatures of the moon. Since so much sunlight is reflected, the heat necessary to warm the ice and create a subsurface ocean must come from a different source. Like Europa, Enceladus is also heated by tidal stretching from the gravitational forces of Saturn. Because Enceladus is so small, these tidal forces easily crack the interior of the moon like an egg, causing molten material to flow out and warm the ocean beneath the ice. This is where we would expect any hypothetical life to gain its energy to establish an ecosystem. Life on Enceladus would differ significantly from that on Europa, as Enceladus has a greater variety of compounds available besides sulfur from the ocean floor thermal vents. It is possible that hypothetical Enceladine life could rely on acetylene as a metabolic source. Acetylene is a hydrocarbon that has been detected in the ice grains ejected from the plumes of water vapor at Enceladus' south pole. On Earth, there is evidence of one type of bacteria, Pelobacter acetylenicus, that metabolizes acetylene, lending weight to this hypothesis. Another type of life that could exist on Enceladus is methanogens, which would use methane as a source of energy, as this compound is plentiful in the Enceladine Ocean and the rest of the Saturnian system, including Titan. Methanogenic archaea have been successfully cultivated under the same methane-rich, photon-poor environments that are expected on Enceladus. Although anaerobic life is more likely to exist in the oceans of Enceladus, there is a remote possibility for aerobic respiration to occur through iron reduction. This mechanism involves an organism undergoing metabolic aerobic respiration in the Enceladine Ocean by removing oxygen from iron. The moon has a rocky core that may contain iron, but this is more of a non-zero probability than a bold scientific hypothesis or prediction. There are several proposed missions to Enceladus at present, as it is considered to be the most accessible option for sampling life. Some of these missions are privately funded, while NASA has proposed one of its own. The NASA mission aims to send an orbiter to investigate the moon. It will spend 200 days orbiting before finally landing on the surface. Once on the surface, the probe will be stationed near the plumes at the South Pole, where it will attempt to sample them for life and other findings as the water falls back onto the surface. Unfortunately, the mission is not expected to begin construction until 2029 at the earliest and is not set to launch until 2038, with a backup probe to be launched in 2039. The arrival date of the probe to Enceladus is estimated to be 2050. Although 2050 is a long way away, it will come eventually, and by then, technology could have advanced to the point where the mission time becomes half, or perhaps the probe will be able to do more than just sample a few water plumes. In the meantime, while we all wait to go ice fishing on an extraterrestrial world, don't forget to like the video and subscribe if you like this type of content or learned something new. Until next time, my friends.